Let's call this an introduction to three-phase circuits. And from here on out, you will see me use the Greek letter phi like that to represent phase. All right, so in our homes, at least for the overwhelming majority of us, we are used to dealing with what's commonly called a single phase circuit. So in a single phase circuit, we have a system that's going to look something like this. Okay? So here is our voltage source. It's a sinusoidal voltage. So this would be representative of the voltage that's, say, coming out of an outlet in our home, or the voltage that's being applied across the terminals of our main breaker for our home service. All of that is a single phase system usually. And this voltage has some magnitude, which I'm going to call VP, and then some phase angle, theta V. I'm going to put a pair of terminals here. Then we are going to have some wires, right? So I'm going to put a wire across here. And this wire will have some impedance, which I'm going to call ZW. This wire down here will have some impedance, which I'm going to call Z sub N. I've got another set of terminals. And then over here on the right-hand side, I have my connected load, which I'm just going to call some impedance Z sub L. So we can really break this circuit up into three discrete parts. So everything to the left of the leftmost dashed red line is our source. Everything to the right of the rightmost dashed red line is the load. And everything here in the middle is what would commonly be called a transmission line, because it's for transmitting power across a distance. Okay? Now, I'm going to introduce you guys to a little bit of nomenclature here, or really like how we're going to look at things. So anytime we're on the source side of a circuit, I'm going to use lowercase subscripts. So I might put a terminal here, lowercase a, and a terminal here, lowercase n. And then when we're on the load side of our system, we're going to use a capital letter. So uppercase A and uppercase N. So if we were to crack open our breaker panel, really what I'm trying to represent here would be our hot wire. And then here down on the bottom would be our neutral wire. Okay? So this is the basic parts of a single phase system. We have some sort of voltage source. Like I said, could be as simple as an outlet, might be a single phase transformer or something like that. We connect to that voltage source some wires, and then we connect our load to the other end of those wires, and we've completed our circuit. So this is perfectly acceptable for delivering moderate amounts of power over short-ish distances. But for long distance and for large amounts of power, typically a three-phase system is used. Okay? So our three-phase system is going to have a similar makeup. There's going to be a source side, transmission lines in the middle, and then a load side. But instead of having a single voltage source, we're instead going to have three voltage sources. Okay. So we might choose to represent that type of system like this. So here's one voltage source. Here's another voltage source. Here's a third voltage source. I'm going to call this lowercase a terminal, lowercase b terminal, and lowercase c terminal, like so. Here are my transmission lines. So I'm going to have an impedance ZW here. Let's say another impedance ZW here. And a third impedance ZW here. Realistically, there's nothing that's forcing all three of these impedances to have the same value. That being said, without them all being the same value, we have what's called an unbalanced system, which is significantly harder to analyze and understand. So for the intents and purposes of this class, we're going to be dealing with just balanced systems. And then over here on the right-hand side, we have our load. And so this would be the load connected to the A phase. So that's why it has ZLA. The load connected to the B phase, ZLB. The load connected to the C phase, ZLC. In a balanced system, all of these impedances will also be equal. We'll talk about that more in a little bit. So here I have capital A, capital B, excuse me, capital C, and that doesn't look as capital as I want it to be. The point of interconnection over here on the left-hand side, where the negative polarity terminal of all our sources tied together, is what we typically call the neutral terminal. However, I want to be clear that not all three-phase systems will actually have a neutral conductor in it. So over here on the right-hand side, we're going to have a neutral terminal for our load as well. And then once again, we can just subdivide this. So everything to the left is our source, everything to the right is our load, and there in the middle, we have our transmission lines. So I'm going to ask you guys a potentially odd question. I don't know if any of you will be able to answer it, but why is it that we use three-phase power to transmit power over long distances? For what it's worth, technically speaking, the answer is literally in front of you on this screen.
And it's more efficient,
What do you mean by more efficient?
because when you have three different phases, like something with the phasing over the frequency, like the peaks, there's more peaks, you know what I mean? So instead of like, I know in single phase, like high, low.
So if you were talking about delivering power to an induction motor specifically, and even then it wouldn't necessarily be efficiency. As we'll see in a couple of days, the average power and the instantaneous power delivered in a balanced three-phase system is actually constant. So if we connect a motor to a balanced three-phase system, it will have a constant torque, which is actually a pretty huge deal, because effectively that means that since the power hitting the motor isn't surging, it's not going to vibrate. So that's one of the reasons why three-phase motors are used, is because they provide a fixed output and they don't undergo really that many mechanical vibrations, so that they last a really long time. There are induction motors downstairs in the in the power lab in Nefkin Hall that were built prior to World War II, and we still use them because it takes a tank to kill one of those things. They're built so rigidly and they will last forever if you don't go screwing around with stuff. But that's not what I'm talking about here. Okay. Why do we choose to send power over long distances using three-phase systems?
It
Caden.
reduces the amount of time power to zero.
Nope. Nope.
If one of the, here, so if one part goes down, then it still has other parts to rely on for power storage.
Also nope.
If there isn't a whole lot of loss when you're traveling that distance.
So it does have, so the reason why we typically use very, very high voltages when we're transmitting three-phase power is to minimize the losses, but that doesn't answer the question that I'm looking for, right? So that's regarding minimizing resistive losses in our cables. So effectively, the higher the voltage that we have, the smaller the current that we will have. And so we will have smaller, what are called I squared R losses, which is literally just our conductors are heating up because they're carrying current. So if we can get the system to carry less current, but the same amount of power, which is what transformers do, then we can minimize our I squared R losses by just boosting the voltage really high. So over very, very long distances, like driving between here and Mississippi, or particularly between Monroe and Mississippi, you might see those very, very large towers with the wires way spread out. So that's like, I think it's 145 kV system, 145 kilovolts is what's being distributed over there, I believe. Still doesn't answer my question. So I will answer it for you. Notice here, so our load in this case is absorbing some amount of power. Let's just call it P load, right? And it takes two wires to deliver that power P load to our load. Well, in this system down here, we have three loads, which are also absorbing some power P load, but it only takes three wires in total. So it's economically significantly cheaper because it costs less money for conductors. You can deliver more power using fewer conductors, so it's cheaper for the utility company. It's a less infrastructure cost. That is the predominant reason why three-phase power is used. An additional benefit is what I talked about earlier concerning induction motors and all of that kind of stuff, to where you get a constant power output, which means any connected motor undergoes the smallest amount of mechanical vibrations as possible. So now let's talk about how our three-phase voltage is generated, okay? Because this is something that's very interesting, because it's a physical part of our generator machine that winds up giving us three voltages with a very, very specific relationship, okay? So three-phase voltage generation. So I'm going to draw a picture here, and I'm going to try to make it as not shitty as possible, but it's going to be kind of shitty because I can't draw circles to save my life. Okay. So I'm going to put in gray here. This is usually a big metallic thing. A circle. Stylus being a jerk. Yeah. So this big thing right here is what's called the stator of a generator. And the stator is literally just a fancy word that we use for the stationary part of a cylindrical electrical machine, okay? So embedded into the stator are going to be coils of wire. So I'm going to have a coil right here that I'm going to call A. And then I'm going to have a coil down here that's going to be A prime. And these are really just two parts of the same coil. So one of them is the send, one of them is the receive kind of thing. So if I might put something like this, like a dot in the middle of this wire, that means that there's current flowing out of the page. And if I put an X down here, that means there's current flowing into the page. And this constitutes one full loop. Each of these separate things are referred to as a pole on our stator, right? So right now I have the A phase conductors 180 degrees away from each other, okay? Now, physically, 120 degrees out of phase, we're going to see our B phase conductor. So that would be here. And then I'm going to put the B prime, so the negative pole, over here. And then 120 degrees out of phase with that, I'm going to put my C and C prime poles. And we're going to wire these things up such that I have, let me draw this line a little bit straighter, access to my A terminal here. My B terminal down here. My C terminal here. And then I'm going to tie all of those primed poles together. So this is jumping over like so. This guy's jumping over like so. And then this guy right here would represent my neutral terminal. Okay, so here's the stator. Here are the electrical connections. Internal to this thing, we are usually going to have an electromagnet, okay? Excited with a DC current, and that's what's called the armature. But because we're not in an electric machinery course, I'm going to dumb things down a little bit. And instead of putting an electromagnet in, I'm going to put a permanent magnet. That has a specific north and south pole. And I'm going to mount this magnet on a shaft such that it can spin in a counterclockwise direction with some angular frequency, omega. How many of you guys have had Physics 202? Handful of you. All right. So what happens when a coil of wire sees a changing magnetic flux? A voltage is induced. That is exactly what this system is doing, right? So all of my coils of wire are stationary, but my magnet is constantly spinning because I've got it connected to some sort of mechanical system, which could be part of a hydroelectric plant or something like that. That's just as water passes through, it causes the rotor here to spin. And so because my magnet is constantly spinning, the amount of magnetic flux that each of my coils sees is constantly changing. So I'm going to wind up inducing voltages across each of my coils. So I'll have some voltage here between the C phase and the neutral conductor that I'll call VCN. I'll have some voltage here between the B phase and the neutral conductor that I'll call VBN. And I'll have some voltage here between the A phase and the neutral conductor that I will call VAN. And so what we should expect to see is something like this. So I'm starting with my A phase having no specific phase angle. So we might see something like this, where the peak value of the A phase voltage, so I'm going to put VAN as a function of time, is going to be VPA. So this is the phase voltage on the A phase cosine omega t. And that's going to happen when the north pole of the magnet is right over here. Okay. Well, at that time, the flux, yes, Michael.
The thing is that this motor has 3 wires, generates AC, like, just by spinning it.
Yeah.
So cool.
It is indeed very, very cool, right? So
there's no electronics that need to regulate it, like just get AC right out of it.
Mhm.
Okay.
So let's talk about that here really briefly, right? So effectively what's happening is that we have a magnetic field that's constantly rotating among all of these coils, right? So the field that each coil sees is going to be at its maximum when the poles of the magnet are perpendicular to the surface bounded by the coil effectively, okay? So that's what I was saying, like when the north pole of the magnet is pointed over here, the A phase is going to see the most magnetic flux. As it spins, it's going to see less and less flux. When the north pole is right here, it's going to see no flux whatsoever. When the north pole comes over here, it's going to see the same amount of flux that it saw over here, except that it's going to be in the opposite direction, which means the induced voltage is going to have a change in sign. And then when it's back up here, it's 0 again. So because we're spinning this magnet with a specific angular frequency, the induced voltage is going to be a sinusoidal voltage, okay? Which is exactly what I have depicted. Now, the B phase is physically 120 degrees around the circle of the rotor away. We can see from how I've drawn this thing spinning that if the A phase is at its maximum here, the B phase is going to be at its maximum about right here, which is later than the A phase, right? Because of the direction of our rotation. So the induced voltage on the B phase is actually going to lag the induced voltage on the A phase by exactly 120 degrees, because there is physically 120 degrees of separation between those coils. So that should look something like this. So let's see, so that's 90. So peak value about right here. That looks shittier than normal. And so we'll see that VBN of T is VP sub B, so whatever induced voltage we have, magnitude times the cosine of omega t minus 120 degrees. And then our C phase is lagging behind the B phase by an additional 120 degrees, again, because of the physical separation of our coils, right? So that means its peak is going to be about right here. Where VCN of T is VPC times the cosine of omega T minus 240 degrees. This minus 240 degrees, you might see it in some textbooks as plus 120 degrees because those are the same angles. I'm always going to use negative so that we always understand that the B phase is lagging the A phase by 120 degrees and the C phase is lagging the A phase by 240 degrees, okay? All right, so we now have an understanding of how we get these three different phase angles. So if all of the coils that are used are made of the exact same type of wire and the exact same length, then the induced voltages are actually going to be the same as well. So they will all have the exact same magnitude. So I'm now going to get rid of this A, B, and C. And from here on out, we're going to assume that all three phases have the exact same magnitude because the machine itself is manufactured in such a way to have a consistent number of windings in each coil, a consistent length of wire, et cetera, et cetera. So we would have to physically mess the machine up in order for there to be any significant variation in the magnitude of these voltages. Yes?
You're talking about a balance system?
Yep. So in a balance system, the magnitude of our voltages generated by our generator will all be the same, and everything will be exactly 120 degrees out of phase with the subsequent phase. Yes? So an unbalanced voltage source doesn't really exist. And I say that because it literally requires errors in the manufacturing to generate. As long as the system is built consistently, you're going to have a balanced three-phase generator. So the voltage that you're being provided will be balanced. The unbalance is then going to come from any change in impedances that are connected. So if we used a different gauge of wire to connect the A phase to a load as opposed to, so if let's say that we used 18 gauge wire to connect the A phase of the source to the A phase of the load and 8 gauge wire to connect the B phase of the source to the B phase of the load. Because those wires have different cross-sectional areas, they are going to have different resistances, and therefore there is going to be some imbalance in the system. On the load side of things, we could just effectively have something plugged in between A and neutral and something not plugged in between B and neutral to generate an imbalance.
Why three-phase? Not 4 or 5.
So some countries do use, so it's, I haven't heard of 5-phase. 4-phase is a thing where everything is just 90 degrees physically out of phase with each other. I think 3-phase is kind of the sweet spot for manufacturing tolerances as well as making the math not super duper horrifying. That being said, on the load side of things, effectively, like you'll see 3-phase loads with 2 poles like we have here, but you'll also see like 3-phase loads, but instead of having 2 poles, they might have 4 poles or 6 poles or 8 poles or whatever. So it's looking like it's a 6-phase system, a 9-phase system, a 12-phase system, etc., all that translates to is that the rotor spins slower because it doesn't have to make a full revolution before it hits the next peak value. So a 3-phase, 2-pole system like this, so if we effectively flip this system around to where this was a motor, this thing would spin here in the United States at 3,600 RPM because it's a 3-phase, 2-pole motor. If it were a 3-phase, 4-pole motor, it would spin at 1,800 RPM because it only has to go half a revolution before it catches the positive peak of the A phase again, like that. So anyway. All right. So here's how our voltages are generated, and then hopefully super obviously, all of these can be converted into an RMS phasor as well. So we might have some RMS phasor voltage that's AN, that would just be VP divided by the square root of 2 with an angle of 0 degrees, and so on and so forth. So VBN would be VP root 2 angle negative 120, and I'm running out of room, so we'll just stop it there. But our phasor voltages are obviously going to be 120 degrees out of phase with each other, and they are going to have the same phasor magnitudes as well. Okay. All right, so this particular sequence is what's called a positive phase sequence. And it's a positive phase sequence that goes from A phase to B phase and then to C phase. Negative phase sequence is just what we get when we spin the rotor in the opposite direction. So instead of going A, B, C, it's typically called a CBA phase sequence. Okay. And it's literally just means that now, instead of the B phase lagging the A phase by 120 degrees, the B phase would lead the A phase by 120 degrees. There is literally no other difference between a positive phase sequence and a negative phase sequence system. It's just the direction that you spin the rotor. Okay. So because there's no appreciable difference between the two, we are going to assume that everything that we deal with in this class is a positive phase sequence system. Okay. All right. So now let's talk about our source and load configurations. And this is where things are going to start to get a little bit confusing. Okay. So let's talk about what's commonly called a Y, or literally just the letter Y, connected source. So on the left, I'm going to draw how this is typically depicted in textbooks, which I find wildly annoying. So I'm going to also redraw it in a way that helps me sort out the circuit analysis part of analyzing these 3-phase circuits, okay? So I'm going to start with the neutral conductor directly in the center. And I'm going to make a note here that this is technically optional. So we don't necessarily have access to the neutral terminal, even if our source is Y connected. Now I've got a voltage source here. This is going to be my B phase. And because this voltage is measured between the B terminal and the N terminal, I'm going to call this voltage VBN. I'm going to have a voltage source over here. Because it's measured between the A terminal and the neutral terminal, it's going to be called VAN. And then down here, I have yet another voltage source. This is my C terminal. This is voltage VCN, like so. So this is the way that it's typically drawn, and having all of these weird diagonal voltage sources annoys me. So instead, I'm going to draw it exactly like I drew it before. This is my neutral conductor. Here's the A terminal. B terminal. And the C terminal, which makes this voltage VAN, this voltage VBN, and this voltage VCN. And here is my optional neutral terminal for connecting a neutral conductor to the system. All right, so is everybody okay with how these two circuits are equivalent to each other? I have a voltage source connected between the A terminal and the neutral terminal, the B terminal and the neutral terminal, and the C terminal and the neutral terminal on both sides. So even though they look very different, electrically, they are the exact same thing. Okay. All right, so here's where we're going to get into some definitions, and this is where the trouble really begins. Okay, so a phase voltage is going to be a voltage drop over, excuse me, one phase of a source or a load. So for this Y-connected source, our phase voltages are simply our voltage source voltages, VAN, VBN, and VCN. Now, another type of voltage that you might hear about in a three-phase system is what's called a line voltage. So a line voltage is just a voltage drop between the transmission line terminals of a source or load. So I'm going to draw these in green. So this voltage that I'm putting right here, VAB, would be a line voltage because it's measured between the transmission line terminals associated with the A phase and the B phase. Okay. This voltage right here VBC is also a line voltage because it's measured from one transmission line terminal to another one. And then lastly, our commonly used line voltages would be VCA, so measured from the C phase to the A phase terminals. On our alternative representation, we'd have VAB like so, VBC like so, and VCA like so. So in a Y-connected source, the phase voltages and the line voltages literally represent different quantities. Okay, but that's not always true, which is why things get quite confusing. Okay, so now let's talk about a phase current. So a phase current is simply a current flowing through one phase of a source or load. Oops, let me move this down. I didn't list out my line voltages below that, so I'll come back and do that in just a second. So let me write these in green. So these would be VAB, VBC, and VCA. My apologies. For my phase currents, I'm going to represent them on the graph in red. And I'm going to do something that's a little odd here. I'm going to choose to have all of my currents flowing in such a direction that my source is absorbing power. Okay. And the reason I'm doing that is just so that I'll be consistent for everything. Anytime I draw a phase current, it will be from an absorbed power perspective, regardless of whether it's from a source or on a load. So my phase current would be this current, IAN. This current, IBN, or this current, ICN. Have you guys caught on to the subscript notation that I'm using? So for the voltages, it's pretty straightforward. Whatever the first letter in the subscript is the positive polarity terminal. Whatever the second letter in the subscript is the negative polarity terminal. For our currents, it's effectively where it's flowing from to where it's flowing to. So a double subscript notation is very commonly used for all voltages and currents in three-phase systems. So here on this representation, we would have our phase current IAN, our phase current IBN, and our phase current ICN. Now let's define line currents. So a line current is simply current flowing through a phase of the transmission line. Since our source here is open circuited, I can't actually represent any line currents here. But the line currents would be the currents traveling down the A phase, B phase, and C phase of our transmission line in a closed network. So once we start looking at a big picture thing, the line currents will be all over the damn place. Yes, totally. So going from, so if we had a system, I can show you up here. This would be a line current. So this current I lowercase a capital A would be a line current because it is a current flowing down the transmission line from the source to the load. So yes. All right, so these are the basic terminologies that I'm going to use. However, there's also a couple of other things that you might hear. So these voltages, VAN, VBN, and VCN will commonly be called, so let me write this out. Commonly called phase to neutral voltages because they're measured from one phase conductor to the neutral conductor. Isaiah. Because that's only true if we're considering the phase currents in a Y connected source, and you'll see why in a minute. Things are about to get even more confusing when we talk about a delta connected thing here in a second. So, and you'll see why I can't just say a phase current is the opposite of a line current. So VAN, VBN, and VCN are also commonly called phase to neutral voltages. VAB, VBC, and VCA are also commonly called line to line voltages. So at this point, we have effectively 4 different ways to describe voltages in a portion of this system. Okay, so I'm trying to be as clear as I can possibly be about what the distinctions are between all of the different ways that we choose to call these different signals. Okay, I truly believe that the nomenclature is the hardest part of this material. Okay? So I try to specifically stay with these 4 things. I'm going to try not to use the terms phase to neutral or line to line at all so that it's always clear exactly what I am referring to. But in industry, you will very frequently hear the term phase to neutral or line to line voltages. Okay. So, all right, so now let's look at a delta connected source so that I can explain to Isaiah why we can't just call a phase current the opposite of a line current. Yep. You are special, bud. All right, so here's a delta connected source. So because this voltage is between the A and B terminals of the network, I'm going to call it VAB. I'm going to put a voltage here that will be between the B and C terminals of the network. So this will be VBC. And then I'm going to have a voltage here between the C and A terminals of the network. So this will be VCA. So this is my traditional representation, which I also find incredibly cumbersome to use. So instead, I'll usually depict it like this. So this voltage would be VAB, this voltage would be VBC, and this voltage would be VCA. Okay. So our definition for a phase voltage is never going to change. Okay. So phase voltage is always just the voltage dropped across one phase of a source or a load. So for this particular circuit, what do you think our phase voltages are? So each of those voltage sources represents one phase of our source. So they should just be the voltage source voltages, right? So VAB, VBC, and VCA are our phase voltages. What are our line voltages? So by definition, our line voltages are the voltages measured between the transmission line terminals. The exact same thing. So we'll have a line voltage VAB like so, a line voltage VBC like so, and a line voltage VCA like so, which means for a delta connected source, the line voltages and the phase voltages are literally the same thing, but in a Y connected source, they represent entirely different signals. Starting to see why this is confusing, right? So here's our representation on my preferred way to draw these. Sorry. Now, let's put our phase currents. So phase currents, by definition, are the currents flowing through a single phase of our source or load. And I'm always going to draw them in such a way that we're getting absorbed power. So this is my A phase current, IAB. This is my B phase current, IBC. And this is my C phase current, ICA. Let me represent them over here really quickly. And now I can answer Isaiah's question. So our line current is the current that's leaving one of the terminals of this network. Kirchhoff's current law in a delta configuration tells us that that line current is going to be equal to IAB minus IBC, which definitely is not just negative one of our phase currents. So it really depends on how our system is connected as to whether our line currents are equal to our phase currents or whether our line voltages are equal to our phase voltages. So we're going to have to constantly be paying attention to how our system is connected as a whole in order to sort out what quantity we're actually trying to figure out. Okay, that's where this gets confusing. So that's why I'm spending an entire day just talking about the jargon effectively. So I have everything defined for my delta connected source now. Any questions on this before we move on to the load side of things? All right. So now let's talk about a Y connected load. So because we're on the load side of the system, now all of my subscripts are going to be capital letters. So putting my neutral terminal here. Might have something that looks like this. Where all of these boxes are just generic impedances. So I might call this one ZYA, this one ZYB, this guy over here, ZYC. In a balanced system, they would all be equal. In an unbalanced system, one or more of them are not equal to each other. So that's one way to represent it. My preferred way is like this. And once again, we may have an optional connection to our neutral conductor. So what do you guys think our phase voltages are going to be? Okay. Just the voltage drops over the impedances. Absolutely correct. So tell me what those should be. So everything that we've been doing to this point has been using a double subscript notation. So how about you hit me with a second subscript for each of those voltages? N would be the second subscript. Absolutely correct, Isaiah. So we would have a voltage V capital AN, V capital BN, and V capital CN, representing this voltage drop, VAN, this voltage drop, VBN, and this voltage drop, VCN. Over on this side, VAN, VBN, and VCN. Okay. Line voltages, what are those going to be? Yeah, the exact same thing that we had for the source, except that we're going to use capital letters because we're on the load side of the system. Absolutely right. So here's VCN. Here's, oh, I screwed that up. VAB. VBC. And VCA. And lastly, we'll have our phase currents. So that's going to be this current, IAN, this current, IBN, and this current, ICN. Anybody have any questions about the Y connected load? The exact same thing as the Y connected source, except that it's flipped over to the other side of the system and all of our voltage sources were replaced with impedances. Isaiah, I think you were raising your hand. So typically, if you look in most textbooks, the current is the current that's flowing to the right, kind of thing. So for the load, it's always, actually, I think a better way to put it would be for the load, it's absorbed power, and for the source, it's supplied power. Is typically how they're drawn, but I don't particularly care for that because it's inconsistent between the source and the load. So I just choose to do everything as absorbed power. All right. Any other questions? So we've got one last thing to do here, and we've got about 7 minutes to do it. Unsurprisingly, I think this will be delta connected floats. So that's going to look something like this. Let me scooch this down. So this impedance is going to be Z delta A. Between B and C, we'll call this guy ZB, and between C and A, we'll call it Z delta C. Our other representation is going to be something like this. So I forgot to actually draw the impedance. So here's A, B, and C terminals. Here is Z delta A, Z delta B, and Z delta C. Our phase voltages are VAB, VBC, and VCA, like so. Our line voltages are the exact same thing. Um, there's not really a particularly convenient place to put the voltages in green on the way that I've drawn the right thing, so I'm going to leave them off, but they are the exact same thing, so they're up there at least once. And then lastly, we have our phase currents. Once again, IAB, IBC, and ICA. All right, so what we're gonna do next Friday when we return from the Mardi Gras break is we are going to analyze a balanced YY system, right? So there's really only 4 different types of circuits that we could ever see. A Y connected source connected to a Y connected load, a Y connected source connected to a delta connected load, a delta connected source connected to a Y connected load, and a delta connected source to a delta connected load. So that's a YY, Y delta, delta Y, and delta delta. We are going to start with a YY system because it's the easiest thing to analyze. And we are going to also be looking at what the consequences of having a balanced system are. Okay. That's going to take us an entire class meeting. The following class meeting after that, we're going to talk about how we can transform any other system into looking like a YY system so that it's easy to analyze and then go back to figure out what particular quantities that we're looking for. So realistically, after we've figured out how to analyze all of the different types of systems, that's when I'm going to start being a pissy asshole about you guys not understanding the differences between phase voltages, phase voltages and line voltages, phase currents and line currents. So for the next couple of days, if something is confusing you, by all means ask. I understand that it is new, but after we've done this stuff for a solid week, I'm going to, I think, pretty reasonably expect you to understand what the difference between these quantities are, and I'll start to be more of a jerk than usual if you don't understand. Just giving you fair warning. Yes. So that's a really good question. For the source perspective, you usually have an option. So like most transformers, if you're using that as your voltage source, are going to have what's called a star configuration, which is really just a fancy word for a delta configuration, or excuse me, a Y configuration, but you're guaranteed to have a neutral conductor. Loads are an entirely different bag of cats, right? So you may have access to a neutral terminal, you may not have access to a neutral terminal. So like one thing that we're going to see, particularly when we get to 3-phase power factor correction, is that 99% of the time you're going to opt to install your capacitor bank in a delta configuration. And the reason for that is because your capacitor bank is going to use smaller capacitors in a delta configuration than it would for the same capacitors in a Y configuration. However, the capacitors also have to be rated for a larger voltage in a delta configuration. So we're going to see, once we get to start doing our analysis and all that kind of stuff, that the voltages, like our line voltages and our phase voltages, are going to be proportional to each other by specific ratios. And those ratios are going to help us figure out how to connect impedances for different applications. So there's really not a hard and fast rule. It's application specific. You might do everything in like up here at the very top. I drew this guy right here as a YY system, but it's a 3-phase, 3-wire system, right? If we had done everything, a delta connected source and a delta connected load, it would still be a 3-wire system. So it consumes the same amount of materials, but the voltage and current relationships are going to be slightly different. So if you know that you're going to have a fairly significant amount of imbalance, you probably want a neutral conductor there, because we're going to see that the neutral is actually what's going to carry the imbalance in a system. And it's going to remove some of that current carrying burden from your phase conductors. But we'll talk all about that kind of good stuff when we actually start analyzing things. All right. Thank you, guys. Have a happy and safe break. Try not to get arrested.